Hello, this video is for chapter 3, continuing with the previous online lecture 5. We are still on chapter 3 for histogram. So this is the example of the histogram. If we have this kind of image, which is not visualized good, then we want to enhance the image by using histogram decomposition. So if you still remember, a good image, the pixel value distribution is along the 0 to 255 pixel values. So we can use histogram equalization to enhance an image. So this is the example. We have right image, then when we perform equalization, histogram equalization, we will get this kind of output, which is more sharp and better visualization compared to the original image. Okay, so I just skip this one because it is already discussed in previous online lecture 5. So this is the histogram exercise. You can refer to the example in the previous slide or earlier slides. So from there, try to understand how the histogram work, and then you can continue with this exercise. Okay. So fundamental of we continue where we still at the spatial filtering. In this lecture, we will look at spatial filtering techniques. Okay, now is filtering, spatial filtering. We will learn how the principle of filtering, which is spatial filtering, which is based on the neighborhood operation, smoothing operation, what happened at the edge, correlation and convolution. So this is the basic filter, basic spatial filter. Now we are talking about filter. Just now we discussed about histogram, which is we can enhance an image based on histogram by using histogram equalization. So this one is also part of image enhancement or pre-processing, where we can use a filter, basic spatial filter. The mechanics of spatial filtering are illustrated in figure 3.32. Next slide. The process consists simply of moving the filter mask from point to point in an image. Okay. If we have image, for example, this image, when we want to perform spatial filter, that filter is actually moving from one coordinate to other coordinate, or one location to the other location. This is meant by this explanation. Moving filter mask from one point to point in an image until the end, until all size of the image So at each point xy, the point, the response of the filter at that point is calculated using predefined relationship. Okay. Predefined relationship. So what is the predefined relationship? That is, continue. For linear spatial filtering, the response is given by a sum of product of the filter coefficient and the corresponding image pixel in the area spanned by the filter mask. For the 3 by 3 mask, the results or response are of linear filtering with the filter mask at a point xy in the image is this one. So this is the equation or notation of linear spatial filtering or explanation by this statement. This statement uh, whenever it's given in this mathematical form, so this is the mathematical form to present this statement. Sum of product of filter coefficient. W -1, -1, F, X. W is the mass, F is a function of the image, X is a point to point in an image, so on and so forth, until finally you get the response of R for the whole size. Okay, so you can read the statement or the explanation about the spatial filtering there. But to be more practical explanation, okay, so you can focus on this figure 3.32. Okay, so this is the mechanic of spatial filtering. The magnified drawing shows a 3 by 3 mask and the image section directly under it. The image section is shown displaced out from under the mask for case of readability. So you are given this example, image origin. This is image fxy. This is the size of the image. This is y. This is x. So whenever we want to perform spatial filter onto an image, so that filter is a form of mask. So this is mask. So this mask will be mask will be placed at one point to the other point until the end of the x1 or image origin here, moving point to point. So that's the working principle of spatial filter. Okay. So how the mask work? I mean, so when this mask placed at one point here, how it's work? So this is the detailed mechanic of spatial filter. So this is the mass coefficient W, value of the mass. And then when you mass at one point, then you just multiply to get sum of product with the pixel value of the image. Then you get this one, then you sum up all, and you get 1 V. So that is the explanation by this definition of spatial filter and also the notation of R. Okay, so there are 3 ways to explain a spatial filter. By this figure, by the mathematical equation, and also by the statement, I mean the definition. and you get out. So this is more detailed explanation how the spatial filtering work. So for example, we have this image. So the results of the sum of product of the mass coefficient with the corresponding pixel directly under the mass. Okay, for example, this mass fx1. So you just sum all, then you get this one response at this point. Then move again. Move, move. Okay, like this. This is the mass coefficient or filter coefficient, the value of the filter. Then you map on the existing pixel image. Right? W00. Then you sum all. So the response of at this point fxy, this is the mass, this is the image, multiply, then you sum. Then you get this one. Then move to the other point. Move until finish all the pixels. Okay, so please understand this one because this spatial filtering have the question of calculation. If you don't understand, then you will not get the correct answer. Okay. The calculation. So, okay, this is the more explanation about the spatial filter. So this is the example of image with the pixel value in the form of matrix. Right? So this pixel value is 0 to 5 depends to the image. Okay. So the image represent in a function of fx1. So for example, we pick one pixel here E, but basically if we perform spatial filter to the image, it will start at this location, move point to other point until the end. But this is just to show you the example at this point how spatial filtering do the calculation or the masking of the original image E. But it is actually run into all the value, but because this is just to show you the example, and this I will explain only at this location E. Simple 3x3 neighborhood. So if we calculate or we perform the spatial filtering, for example at this location E, it is actually taking this size, calculate the neighborhood, the calculation of the filter. Look at the neighborhood. So the neighborhood is a B, C, D, F, G, H, I. The pixel or the response of the filter is at this E. So 3x3 filter. So this is the filter or mass coefficient RST UVWXY. Then you get the E here, which is the E is a response of the filter. This is the calculation. Very simple, very straightforward. But if you don't understand, then you don't understand. You cannot solve the calculation of the spatial. So you will get one this E one, but the other pixel move up, move to the next one. The above is repeated for every pixel in the original image to generate the smooth image. So this is the example. So you can try this example. If you can do this correctly, means that you understand. So this is the equation form. Filtering can be given in equation form as shown above. Notation are based on the image shown on the left. Okay, so this is a type of spatial filter, simple averaging filter. This is the type of filter, simple averaging filter. The coefficient is 1/9, all 1/9. So if you perform this 1/9 filter to the image, it means that you are perform simple averaging filter. They call it simple averaging filter. Okay, 1/9. Simply average all of the pixels in a neighborhood around a central value, especially useful in removing noise from image. Also useful for highlighting gross detail. So this is a smooth filter, the same example, but only the real value, 1/9. So this is the example of original pixel value here. The pixel value of this image. Then you perform 1/9, which is this 1/9 is a spatial smoothing averaging filter. Then you get this output E98.33. So this 106, when you perform the spatial filtering, so you will get the output of the filter or response 98 point. So this is, we call it out averaging filter, because the average is 99, 98, 95, 90, 90, this value, so average become 98. Okay, so this is the example of image smoothing using spatial filter. The image at the top of left is an original image of size 500 by 500, and you perform filter size of filter. The bigger the size, the more blur. This is another type of filter. They call it weighted smoothing filters. So this is the value, weighted smoothing. More effective smoothing filters can be generated by allowing different pixels in the neighborhood, different weights in the averaging function. Pixels closer to the central pixel are more important, often referred to as a weighted averaging. 4/16. The rest is 1/16. Weighted averaging filter. Okay. Another smoothing example, by smoothing the original image, we get rid a lot of finer detail, which leave only the gross features for threshold. So this is an example of spatial filter. You have your original image, apply smoothing filter, then through the threshold the image, then you get very clear object compared to the original image. Averaging filter versus median filter. Since this is the original image with noise, image after averaging filter, image after median filter. Okay, filtering is often used to remove noise from image. Sometimes a median filter works better than averaging filter. So this is something happen when we perform spatial filter at the edge. At the edge of an image, we are missing pixels to form a neighborhood, because at the edge you don't have neighborhood, right? For example, if you want to perform spatial filtering at this edge, because we understand that the mass is 3 by 3, and then you only have 1, 2, 3, 4 values. This edge 1, 2, 3, 4, 5, we don't have values, because value is only inside the image, outside. So this is, we call it strange things happen at the edge. Okay. So So there are a few ways how to handle strange things happen. First, only works with some filters. Omit missing filter. Just ignore. Can add extra code and slow down processing. Pad the image typically with either all white or all black pixels with padding. Replicate, truncate, allow pixels wrap around image can cause some strange image artifacts. So this is an example of how to handle edge for filtering. Zero padding, replicate image pixel, wrap around edge pixels. Okay. So the next is a type of filter. We have low pass, high pass, band reject. Okay. Linear versus non-linear. So please take your time to look at this slide and try to find more detailed information in the internet so that you can understand it. Okay, so this is the example of another example of filtering. Moving filter by Gaussian. Okay. Happening filter. So this is the activity in class. This is the last semester assignment. So that's all for chapter 3. We will continue on chapter 5. Thank you very much. See you again.